Hello, sir, and hello, everyone. So today we're going to talk about the path-independent conservative field and potential function. So we're going to talk in the chapter 16, integration in vector field. In 16.3 is the topic that we're going to talk about. So before starting, I'm gonna introduce myself. My name is Kim Sen Il. I'm from Department CE Souvenir, Paragon International University. So table content that we're going to talk about today will be two-dimensional gradient field and three-dimensional gradient field, potential function, gradient, conservative, path-independent, and closed curve in gradient field. So first, we're going to talk about two-dimensional gradient field and three-dimensional gradient field. So two-dimensional gradient field, when f of x and y gradient is their f equal to fx and fy. If we say that a vector field vector f equal to n is a gradient field, then there is some f of x and y where equal to fx and n equal to fy. So how can we tell if vector f is a gradient field? So when equal to fx and n equal to fy, remember that when we differentiate it fx respect to y and fy respect to x, when we put the bracket of sx and we plug in got y equal to an x, and that's when we can tell that vector f is a gradient field. So let's take a look at the example. So in this vector field is a gradient field. So to check xe to the power xy, that is and ye to the power xy, that is un. So we just need to differentiate respect to y. We got x to the power 2 and e to the power of xy. And un we differentiate it respect to x. We got y to the power 2 and e to the power of xy. So y and x is the answer is not the same, so it's not a gradient field. So let's take a look at another example. Vector f equal to 3x to the power 2 plus 3y to the power 2, and that is and 6 xy, that is n. So when we differentiate it respect to y, we got 6y, and n differentiate respect to x, we got 6y. So y equal to nx, which is 6y. So both of it equal to each other. That means that vector is a gradient field. So moving on, the three-dimensional gradient field is just similar to two-dimensional gradient field. We just need to add one more term in there. So vector f equal to and p is a gradient field. Then there is some f of x and y and z, where equal to fx and n equal to fy and p equal to fz. So we just need to differentiate those with different term. Fxy equal to fyz, and we plug the and n in. We got y equal to an x, so fyz equal to fzy. So we just plug the fy of z and fz of y. We got nz equal to py and fxz equal to fzx, and we plug fx of z and fzx. We got mz equal to pa. So let's do the example to check the three-dimensional gradient field. So vector f, so y plus z, that is x plus z, that is n, and x plus y, that is p. So we just need to differentiate respect to y, we got 1, n respect to x, we got 1, and n respect to z, we got 1, and p respect to y, we got 1, and respect to z, we got 1, and p respect to x, we got 1. So when we differentiate all of it, we got the answer is 1. So all of it is equal to each other. That means this vector is a gradient field. So moving on to potential function. So if vector f is a gradient field, how do we find its potential function? So if vector f equal to n, that means it will be equal to fx and fy by doing the integration of dx and integration of n dy. So let's take a look at the example. So to find the potential function for vector f, 3x to the power 2 plus 3y to the power 2, that is and 6xy, that is n. So we just need to integrate it. So we integrate dx, we got 2x to the power 2 plus 3y to the power 2 dx, we got x to the power 3 plus 3xy to the power 2, and we integrate n, which is 6xy dy, we got 3xy over 2. So we can see that this first term is unique and the second term of and n is the same, so we just need to take only one. So the final potential function is f of x and y. We got x to the power 3 plus 3xy to the power 2. So another example of a 3D dimensional gradient field. So vector f, y plus z, x plus z, and x plus y, that is similar to the last example. So we already know that this vector field is a gradient field, so we just need to integrate dx, we got xy plus xz. So we integrate n dy, we got xy plus yz, and integrate p dz, we got xz plus yz. So to find potential, we only take the unique term of the answer when we find the integration of each one. So xy is unique, we take one. Xz is unique, xy is the same, we don't take this one. And yz is unique, and xz we already take it, and yz we already take it. So final, we got xy plus xz and plus yz. That is our potential function. And then we're going to talk about gradient conservative path independent. So if vector f is a gradient field, vector f will be equal to their f. Then we can also refer to vector f as a conservative field. So vector f is a gradient field is the same as vector f is conservative, and this is also the same as vector f is path independent. So vector f is path independent. When we do the integration f dr, it does not change depending on the path taken. That means if it starts from p0 here, we will do the curve thingy to p1, and p0 here and straight to p1, and p0 here, do the curve up to p1. Of these three, it will not change because it's path independent. When vector f is path independent, it does not change. So to do that, we need to do fundamental theorem of line integral. So when vector f is path independent, can use the fundamental theorem of line integral, and this is the formula. So integration of f dr is equal to f of p1 minus f of p0. So we plug in the final distance p1 and starting distance p0. We got the answer of it. So let's take a look at the example. Vector f equal to xy. So calculate the integration along the curve shown. So it's time from 0, 0 to 1, 0 and 1, 1. So we check if this vector is gradient or not. So we just need to differentiate x and y to y and x. We got 1 equal to 1, so that means equal to each other. That means it's the gradient field, and when it is the gradient field, we can say it's path independent. And then we just need to integrate dx, we got xy, and dy, we got xy. So it's the same term, we only take one. That means the potential function of x and y is xy, and then we use the fundamental of theorem in the theorem of integration line. We got f of p1 minus f of p0. So p1 is 1 1, p0 is 0 0, and then we plug in the potential function. We got 1 multiplied by 1 minus 0 multiplied by 0, we got 1. Lastly, we're going to talk about closed curve in gradient field. So when C is simple and closed curve, that means when we use the formula of fundamental theorem, got 0 if vector f is path independent. So for the last example, vector f, x, and y is the same as the last example. That means it is the gradient field equal to 1 and 1, so it's also path independent, and the potential function is xy. But we don't need to calculate it because we just assume that it's equal to 0 because it's a closed curve along the unit circle. Start from here, then it's go back to where it started. That means closed curve. So yeah, it's equal to 0. And that's all for the chapter 16.3, path independent conservative field and potential function. And that's all from me. Thank you everyone for listening, and good luck.